This is Module 2, Part A in our lecture series on commercial building energy auditing. The learning outcomes for Module 2 will be to identify energy efficiency measures and how to calculate them. There's different methodologies used depending on the measure type, and then we'll dive into what constitutes an energy audit report. We left off looking at benchmarking of the facility after looking at utility data, and that was covered on page 32 and 33 of the handbook. And energy efficiency measures are covered on page 59, basically starting. And in between page 33, 32, and 59 are a whole bunch of bullet points that I just wanted to touch upon briefly. And we're not going to go into them in detail. They have to do with actual data collection on the site. So the textbook talks about the site visit, how to prepare for that, and the pre-assessment interview. That's where you talk to the facility manager typically and ask some detailed questions. There's a bit upon taking photographs. The energy auditor, one of their biggest tools, of course, is the camera, and photographs are really useful, and there's a whole bunch of information on how to take successful photographs. The building automation system, we always try to look at the BAS if we can, because that gives us some information upon set points, on, off, how things are running, what kind of systems they have out there. And then there's some preparation activities, and then there's the initial walkthrough. Some people do a real quick walkthrough just to sort of get the lay of the land. And then the textbook goes into more detailed audit procedures, practical arrangements for site work. And then once you've collected all your information, you're going to do an exit briefing. And we always do this at the end of the day. Once we've been through all of the places that we're going to go at the facility, then we sit down and we have a debriefing essentially and try to collect our notes, talk with the facility folks and see if they have anything that they want to tell us about. Safety is covered. That's a real important issue. A lot of energy auditors need to go up onto the roof. If they're going to be doing some data logging, they need to get into some electrical components. And so safety is discussed also. That's a very important component. And then some of the measurements that may be taken. There could be data logging. Besides photographs, you may collect some spot measurements and things like that. So all of this stuff here, I'm not going to go into a whole lot of detail. That's more hands-on how to collect data at the site. We're going to talk about EEMs, or energy efficiency measures. There are other terms that are thrown about for energy efficiency measure equivalent: energy conservation measure, energy conservation opportunities, and there's more out there. But ASHRAE has selected energy efficiency measure, the acronym being EEM, as the phrase most descriptive of the actions and equipment by which building energy efficiency is improved. And because that's what ASHRAE says, that's what we'll use going forward. So the energy efficiency measure is a collection of actions and equipment installations that are designed to reduce the building's on-site energy use. Operations and maintenance is sometimes included with or assigned as energy efficiency measures. Some reports will say these EEMs are O&M. Basically what they're saying is that we're not changing the equipment, but we're changing how the equipment is operated. For instance, a fan may be running 24/7, whereas it could be shut off at night. That would be an operational change, which is also an energy efficiency measure. So they're often lumped together, but in some reports, sometimes they will show operations and maintenance measures, those that require no cost, just something to change in the operation of the facility, as an energy efficiency measure. Maintenance is the preventive, predictive, scheduled actions preventing failure or decline of equipment. And that's thrown in together with operations and maintenance. Another type of energy efficiency measure is what are called capital investments or capital improvements. And these would be the type of improvements that would replace existing equipment with more energy efficient equipment. For instance, changing out cast iron boilers to condensing boilers, changing the type of chiller, maybe even changing out a system that uses constant volume airflow to variable airflow. Those are significant changes in equipment and usually involve high investment first cost. Some other significant changes that would be considered capital investments would be changes in the building envelope. Upgrading windows or walls, adding insulation or replacing windows, those will save energy, but their investment is very significant. And then another area that would be considered a capital investment would be the installation of solar PV. Again, saving energy, but it takes a significant outlay of cash in the beginning, first cost.
Now I want to look at calculations for energy savings. Really, what we should be saying is estimating for energy savings, because basically that's what we're doing. We're estimating what the energy savings would be based on the energy efficiency measures that are implemented. I'm going to break them calculations down into three categories: the simple spreadsheet type calculations, degree day methods, and bin method, a little bit more complicated, and then the most sophisticated and complex type of calculation would be the energy modeling or simulations. I think the best way to dive into this is to start with a simple calculation, and lighting is a really good example. So let's look at what the energy savings would be in an example where we change the lighting power density and we're replacing T8s with LEDs. So of course this isn't a course in lighting, but I wanted to throw out a couple terms for you. T8 refers to a type of fluorescent fixture. The T and the 8 have a specific meaning. T stands for the tube, and the 8 number refers to the diameter of the tube in eighths of an inch. So a T8 has a diameter of 1 inch. A T12 has a diameter greater than an inch, and a T5, 5/8 of an inch diameter tube is less than an inch. That's about all you're going to get out of me. And they're very common, of course. So let's assume we have a application where we have T8 fixtures and they have 32 watts per lamp and 2 lamps per fixture. Lamp is a term that means the bulbs or tubes, and the fixture is the whole thing. And so it might look something like this, maybe 4 foot long, and each one of these have 32 watts. So this fixture has 64 watts in it. So if you went into a room and you counted up all of these light fixtures, then you could do the simple math. You could say, okay, I have 32 watts per lamp, 64 watts per fixture, and then multiply it by the number of fixtures you have. LPD, lighting power density, is the watts per square foot. So you would have a certain number of these fixtures in a room, and the room had a certain size of dimensions in square feet, and you would take the watts divided by the square footage, and you would get lighting power density. A lot of the codes right now are specifying the lighting power density allowed in spaces. Retail has a higher lighting power density that's allowed than in, say, a classroom or an office. And again, that's lighting design and outside of the scope of this class. But efficiency increases when you lower the lighting power density. So if you went from 2 watts per square foot to 0.5 watts per square foot, you would go up in efficiency of your lighting. So as an example, let's say we have a room that's 100 feet by 100 feet, pretty large, and the lighting power density is 2 watts per square foot, and the lights are turned on from 8 a.m. to 4 p.m. So we can ask 3 questions about this. What is the daily demand in kW? What is the energy use for a full day, kilowatt hours per day? And what is the energy use for a week kilowatt hours per week. Well, the demand is found by taking the lighting power density and multiplying that times the square foot. And we can see that right here. And if we look at the units, 2 watts per square foot times the square footage of that space, then we get 100 times 100, or 10,000 square foot, and we had 2 watts per square foot. So when you multiply that out, what we get is watts, 20,000 watts, or the demand is equal to 20 kW for that space. To find the energy use, we take the demand and multiply that times the hours that the lights are on. So graphically, this is what we have. We have time. So this is 8 a.m., 4 p.m., and then the next day 8 a.m., 4 p.m., and so on. And then on this axis, we have the demand, which is kW, 5 kW, 10, 15, 20. And so if we have 20 kW of lights on from 8 a.m. to 4 p.m., graphically it looks like this. And so what we do is we take the demand, the kW, times the hours that the lights are on, 8 hours, and we multiply those and we get 160 kilowatt hours. And that's the daily energy use. And if we wanted to find the energy use for a full week, we would simply multiply this chunk of time, 8 hours per day, times 5 days per week. And you could do that for the whole year. You could do that for any increment of time that you are looking for. So you would have, for this one, you would have the energy use for a week would be the 160 kilowatt hours in this time period times 5. So in this example, there's basically 2 ways of this existing condition that we can save energy. One, we can reduce the lighting power density. We can go from T8s to LED, or we can reduce the time that they're on, reduce the on time, for example, using occupancy sensors. So written mathematically, we have the energy, kilowatt hours, is equal to the demand in terms of kW times the time in terms of hours. So if we reduce the demand, then we would reduce the kilowatt hours. Or if we reduce the hours on, we would reduce the hours, and so we would reduce the energy. And graphically, what I've shown here is that, let's say we reduce the lighting power density from 20 kW down to 15, then this would be our new energy use for that day and each day consequently. And what if we were able to shut the lights off for one full day? We would reduce the hours by 8 hours in that week. Let's do an example of how we calculate the energy savings over a period of time. In this example, we're going to have new lighting that will reduce the lighting power density from 2 watts per square foot to 1 watt per square foot. The lights are on from 8 a.m. to 4 p.m., Monday through Friday, and this is the room area of 10,000 square foot, which we talked about before. So how much energy can be saved in 1 week by going from 2 watts per square foot to 1 watt per square foot? I'll agree, this one is really simple, but I want you to see the process also, which is really important. So our existing energy use is the 2 watts per square foot times the 10,000 square foot times 8 hours a day times 5 days a week. And then this is a large number, so we're going to convert it from watts to kW. So we divide that by 1,000. We get the existing energy use is 800 kilowatt hours. And the proposed energy use going from 2 watts to 1 watt is 400 kilowatt hours. And so, of course, the energy saved is 400 kilowatt hours. Again, this was a really simple example, but what's important is the process that we went through here. First of all, it's always important to keep track of your units. I see a lot of people, they get carried away, they do this kind of quickly, and they get messed up with their units. And also, when we present this to a client in an energy audit report, we always look at the existing use and then the proposed use and then the energy saved as the difference between those two. And my last comment on this sheet is I always show the calculations that I do in the simplest form with the units. And for those of you that are algebraically inclined and mathematically comfortable, the energy saved, you may have picked up by now, is the area under this curve right here. This was the existing energy use. This is the proposed energy use for 1 day. And so the energy saved is the area under the curve, the hours times the demand. In this example, we have occupancy sensors, and the energy auditors made an assumption that the occupancy sensors could reduce the on time for lighting from 8 hours per day to 6 hours per day in this room. And so how much is saved in a week? So we have the same equation here, but now we're going from 8 hours a day to 6 hours a day. So we're going from 800 kilowatt hours to 600 kilowatt hours. So the energy saved is 200 kilowatt hours. And graphically, that looks like this, where we had the 8 hours per day, and we still have the same demand, but we reduce the on time. Now, of course, you could do both. About that, when we do energy audits, oftentimes we separate the energy efficiency measures because we want to show the effect of, let's say we wanted to show the effect of changing out lamps that reduced our lighting power density from 2 watts per square foot to 1 watt. We would do that calculation separately from the occupancy sensor calculation. Even though you could do them together, it's typically separated because the cost estimates are different, and they are usually categorized as 2 different energy efficiency measures. So I have a couple assignments for you that will take you through calculating energy efficiency measures. Assignment 2A is a lighting retrofit. There's actually 2 of them. The first one is to replace existing lighting in a retail space where you're going to take compact fluorescent fixtures and replace them with LEDs. And the second one is to do the calculation for installing occupancy sensors in some offices. And I provide you with the information you need for calculating each one of those in the setup here. And here is the information that you will provide when you submit this assignment. First of all, don't forget to put your name. You may include the date also, and the energy efficiency measure and the title here. And then you'll state the existing conditions, the proposed measure, and then your results. And I always like to give my results in a tabular form. This is just an example that I copied and pasted from something that I had in my files. And this is my suggestion on how you might want to present your results. Be sure to clearly state your calculations and any other methodology you used, and show your units and state your assumptions. This is actually really important, and I'll show you an example of how I present this. So what I'm showing you here is a lighting upgrade for a facility, and I describe the existing conditions, I describe the proposed measure, and then I show my calculations in a written format with watts so that the reader knows exactly what I'm doing. I also provide, for this one, it was a little bit more complicated than what I'm giving you, and I had different areas that had different lighting fixtures. And so I actually made a spreadsheet and copy and pasted that here. Yours is a little simpler than that. And then I actually show the calculations results here. And at the bottom, I provide a summary table. And this is made in Excel, which I'm going to show you in a second, but I copied and pasted that also. So that's a suggestion on how to present your data. And what I'm showing you here is an example of a calculation sheet that I do. I do everything in Excel, even when it's really simple. And I recommend that you do the same also, because this is from an actual report and I have tabs for each one of my energy efficiency measures. You, of course, are only going to be having this one spreadsheet, but this is what my spreadsheet looks like. And then it has my setup, my calculations, and my results all on one sheet. That's what I highly recommend, even though you could probably do these calculations much simpler. This is the way that I do it and what I would recommend. So for assignment 2A, you're going to calculate 2 energy efficiency measures. You're going to calculate the energy savings for the lighting upgrade and for the occupancy sensors. You're also going to calculate the simple payback, and let me explain what that is real quick. On pages 74 and 75, the handbook talks a lot about the economic metrics and some definitions that are included in this energy auditing procedure. And it can get very complicated. The simple payback is the simplest economic metric that is used, and it's the cost to implement the measure divided by the savings for a year that you calculate. That's on page 75. What it says is that the simple payback is the length of time needed to pay back the initial capital investment expressed in years. And it also says it's not a sufficient metric for long-term economic performance. And we know that. But it's useful because a lot of early on auditing procedures, when they first go into it, they will do a simple payback. And if something has a simple payback of 20, 30 years, well, it might be so cost prohibitive that the energy savings just don't make sense. And so it gets you in the ballpark, essentially. And if you think about it, it's the cost to implement it in the energy savings per year. And so the units actually come out in terms of year. It's like, how long does it take to pay back that measure? So if you do lighting and you get a simple payback of about 4.9 years, well, that's pretty good. Simple paybacks getting above 10 years might take a little bit more head scratching. It's like, well, do we really want to invest that money because it's got a simple payback of 10 years? There's much more detailed economic analysis, which is way beyond the scope of this class. But you get into life cycle cost analysis and all that other stuff. And that's where if you're going to do a capital improvement or make a huge investment, you're going to go past the simple payback. Well, I'm going to stop it here. You have an assignment to do, and if you are using the handbook, there's a lot of information in the procedures for commercial audits by ASHRAE, and I've given you some ideas on where to find that, and you have enough information to go on. The next video is going to be talking about another type of calculation and another assignment.